Hey guys, a very good morning. I'm audible here.
Yes, sir.
Okay. Okay, we'll just wait for a couple of minutes for everyone else. Okay, all right. So I think yesterday we started talking about neural networks or deep learning in particular. Okay. And the overall idea would we want to continue and want to see a small implementation. And we would like to see how all of this works. Okay. So the key terminology is artificial neural networks. Now, we were talking about neurons, and yesterday I kind of mentioned about this. So sorry, I think I messed one of them, like dendrites at the start, axons are the last one. Okay. The soma is the cell body, and as I was mentioning, it has calcium and potassium channels. Okay. And inherently at the end of the day, as I was showing you with the idea of spikes yesterday, that the charge builds up like a RC circuit, it will empty itself up, again builds up, goes up. And this is how it kind of works. Okay. Now, we do not, or at least in the models that we are going to teach you, it's not that we are copying or we are really going or working with everything that is there, which is present in a biological neuron. Okay. There are things that we love to use and there are things that we will not use. And the idea is it's going to be a little simplistic a model, if you ask me. Although there are other variants of neural networks, which is called spiking neural network. Although that's not a topic of discussion, but they are far more closer to the way biological neurons are designed. Okay. So this idea of overall deep learning, or let's call it artificial neural network, is not really a new idea. Okay. It has been there for quite some time, although it has seen, and I will tell you what success and why did it see all these success in recent years. Okay. So as you might understand, this is the biological neuron, and here all these dendrites and axons are connected with each other. Means there is usually some gap, actually, they are not really touching each other, but that's where the chemical transfer really happens. So these cation channels basically are transferring the charge, okay, or the electricity, if you want to call it. And these things will kind of combine together, although it is not always gonna be in the way that we imagine. It's not always gonna be like an additive, or like it might be prohibitive as well. It might even stop the overall flow of the current, okay, or it may pauses the flow of the current over there. Okay, and here you will have your some base charge already available. So the idea is there is a limitation how much you can charge it. Very similar to way there's a limitation how much you can charge a capacitor. It is not infinite or something. Okay, in picofarads or microfarads, they do mention how much is the farads or capacity to store electrical energy. And after that while there would be a burst of energy, okay, after a while, or if you shunt it, okay, if you shunt it or if you just touch the plate, there would be massive burst of energy, very quick release, okay, a very quick release will happen. So this idea has been taken long back in 1958 by Frank Rosenblatt, okay, Frank Rosenblatt. Okay. And he came up with this idea, or he kind of built up this machine, which we now call Perceptron. Okay. And it is like a very early ancestor of, or the plan. Let me show you the picture. I do have the picture. Okay. So this was one of the earliest designs that they came up with, which is fairly, at this point, it was new in 1958 and 59. People thought that this would solve problems or this would really change the game for them. Okay, but okay, of course, it did not happen like that. But anyways, the simplest idea goes like this. They had weights which are very similar to the parameters we use. You can call them weights or you can also call them parameters. Okay. And then you have your inputs, x1, x2, all the way till xn. Okay. And all of them are kind of getting multiplied by the individual weights. Okay, now in a single one, if you have a single node, like right now you have a singular node, okay. So the bias term, this bias term will be a single term. But later I will show you that we can build this in form of an array, and that will be much bigger, and there would be a different mathematics over there. But you guys could clearly see this, that inherently what we are doing is we are taking the inputs and kind of multiplying with the weights, kind of doing the summation here. And then applying a step function. Now, what is this step function? Step function will look something like this. Okay, so till certain input or negative, till negative inputs or zero input, it is zero, the outcome is zero. And as the moment you go in the positive domain, it becomes, the outcome becomes one. Okay, this is called a step function. So fundamentally what you are really doing is, let me explain this, that we are saying, okay, let's do it like this. Wi xi, okay, we can do the matrix multiplication here, or explain it like this, from I is equal to 1 to n. Plus, let's write W naught separately here and pass all this information through a step function. Okay. So whatever the information comes, if it is in negative or zero, the outcome is gonna be zero itself. Okay. And otherwise, the outcome will be positive one. If the outcome, the input is positive. Okay. So inherently what's happening here is, the way it works, a singular neuron or singular perceptron, let's call it singular perceptron. You have your weights for each one of them, and you have your inputs. You have a summation at the first stage, and at the second stage, you are applying this function, which you can call activation function, okay, which we can call activation function. And this would be your final outcome. As you can understand, the final outcome will be in terms of 0, 1. Okay, the final outcome will be in terms of 0, 1, 0/1. Okay, so it is like a classification. So the way it will work is, let's say you have a classification task that you are intending to do. And this is your data. So it will be able to come up with a hyperplane or a separator between two classes. And on one side of it, it is going to be 0. One side of it, it is going to be 1. That's how it usually works. And this would be called a linear classification, because we can segregate the data. We can easily segregate the data as we like. Okay. And we get our outcome based on that. Now, the problem is, in real world, this is not how things usually are. The data is not linearly separable, because if it was linearly separable, we could have just run simple logistic regression, and we would not have to worry about anything beyond that point. Okay, we would have been like, okay, perfectly fine, it works. So let me give you a scenario of a non-linear separation. This was studied. So perceptron became the rage in 1959, and people started thinking they are going to solve the problem of artificial intelligence. But in 1961, Simmert and Marvin Minsky wrote a paper. I think it was more of a, which has been, it is more of a commentary. Okay. So now they both were, they wrote a book called Perceptron. I think it came out in 1962, but the critique came out in 1961 itself. Okay. So they wrote this book, and this book just demolished the whole idea. Basically, what they explained in very simple way is it will not be able to handle a nonlinear classification. And then they gave a simplest example as possible to prove this. So they took this, one of the simplest separation issues between two classes, which is called XOR or XOR classification. Okay, guys, does anyone knows what is XOR? What XOR exactly means? Yeah, these are logic gates. Okay, just let me remind you. Do you remember the OR logic gate or gate? So, okay, let me explain how this works. So let's say your both inputs are 0, then in OR gate, the input is 0. But even if one of the input is 1, means true, the outcome has to be 1. Or, okay, this is how OR gate works. Now, these logical gates are usually taught in computer science or like people who must have been going through electrical electronics fields, right? Now, XOR is called exclusive OR, and this is a slightly different one. It is gonna be one when both inputs are different. Okay, this is how it works. So this is how the outcome will be. This will be 1 and 1, but otherwise they are gonna stay 0. Okay. If both of them are same, it will be 0. Now this is gonna cause issues because let me show you the data and hopefully you will be able to see this. What if I plotted this? Okay, what if I take this data? One moment, please. And actually go ahead and plot these things. Okay. So guys, please imagine the stars as 1 and crosses as 0. Okay. We can ask you that let's imagine this as 1 and this as 0. Now guys, tell me, by using a hyperplane or a straight line, would you be able to segregate these things, these two classes? Sorry. You guys can reply in the chat also, okay? So you can clearly see there are two classes. X has been called as 0 and stars have been called as 1. Now, with a singular hyperplane or a line, would you be able to segregate these groups? No, not gonna happen. Try this. Take any singular hyperplane, move it anyway, does not matter. You will not be able to segregate the system at any moment. Okay. And this marks to the failure of the perceptron. Because what happens in perceptron is it would only work on a linear separation. Hey guys, just give me one moment, please. One moment. Okay. So this marks a very big problem that Perceptron will not be able to solve this. And this kind of raised very big issue that a perceptron cannot handle nonlinear data. What is it good for, right? Now, of course, a lot of progress happened, and but yes, it did stop. It did stop the progress that was happening in this field, or people excitement that was happening in this field. Okay, so let me show you what really happens and how it will move on at this point. So although Minsky and Sigmoid were not trying to kill perceptron, their idea was to do a mathematical analysis. They were mathematicians, and that's what they did exactly. What they suggested is, yes, it will fail if you have a singular node, but they kind of also suggested the answer over there as well. They said, okay, it might fail at a singular node, but if you were to create multiple nodes and that too in a form of a layers, then things will really change. Okay. This is what they suggested. Now understand, like each of them is like a artificial neural network or perceptron. Let's call it each one as, let's say artificial neuron. Artificial neuron. Okay. Each one of them is an artificial neuron. Now, what is it good for or how it works? Let me explain. And again, each artificial neuron, let me just draw this anatomy as well. So each artificial neuron is fundamentally again same. It has its own weights, W1, W2, and whatnot. Okay, and let's say there is some kind of activation function inside. Okay. Now we will talk about some activation functions which might be useful here. So the idea is the outcome would be the activation function. Let me write the activation function as a phi. Okay. Let me write the activation function as phi. Phi with your W, you can call it Wi to Xi plus bias. Okay, the bias is usually separated. So the bias term. Now guys, if I were to say phi is nothing but a sigmoid function. Okay, does anyone know what is a sigmoid function? So if I were to write sigmoid of Wi Xi plus B bias, this equation on its own or individual one of them just feels like logistic regression. Yeah, logic function, perfectly correct. So this feels like logistic regression, but as I told you, even logistic regression has the same problem. It can only do like a linear separation. Okay, so we'll not trust that. But if just imagining it like this, so the way I like to imagine it is like you take a sheet of paper and let's say you fold it for, even if you fold it initially in a straight line, that's fine. So let's say I were to say or ask you this question, and observe this carefully, please. Okay. That if I take a page, okay, page is your 2D, okay, and ask you to make it like a step function, how would it look like? Wouldn't the page appear like, if anyone has done origami or something, they would understand this very easily. So does this look like a step function to you? The step function looks like this, by the way. Does this page now looks like a step function from the side if you were to notice?
Yes.
Okay, very good. But what if I were to fold it back? What if I were to fold it back and just make it in a regular paper? You will notice that there are two creases in the two creases in the paper. And you can think them as a separator scenario. Okay, this might have created a separator. So the way it would work is maybe one class stays here, particularly on this paper, and one class stays here. And linear separation works perfectly fine, right? This looks like linear separation.
Yeah.
Very good, simple. Now the problem, as I told you, again, of course, all the data is not really linearly separable or something like that. Okay. So that can be a big problem, that most data, a lot of data will not be a linearly separable scenario. So now we need to think, okay, how do we solve this problem? Now, again, guys, I cannot go into the whole story of machine learning because that will take a long time. And if you do not know that, it would even like derail from the discussion. So in interest of not doing that, I'm trying to ensure that we do not go into that direction right now. But the idea is usually someone will say, no, we do not. Okay, don't just I will explain you the idea of activation function. Okay. So this like step function is like a kind of activation function. Okay. So guys, I just want to follow up or kind of proceed on this discussion of the paper itself. And what if I were to tell you that every time you can just do this kind of fold or step fold, but every time you have to rotate the paper. Okay. And based on the rotation of the paper, the fold's direction might change. Now guys, if you do it couple of times, you will start to notice that you start to get very complex shapes. Okay, you start to notice that you just even see, understand, both of the folds are fundamentally like linear, right? But once you combine these two folds one after another, they start to look very nonlinear to you. What it means I'm trying to say here is they will be able to deal, or they might after a couple of times or a few times, they will be able to deal with something which will be very different than whatever we are trying to do. Okay. So the overall idea is you keep bending. So if I keep bending this scale, and so guys, what we are doing with multiple layers, that's the point I want to explain to you. If I have these multiple layers of neurons, why we require multiple layers of neurons? See, understand at each level, I'm trying to tell you that there would be a folding experiment, but because of these weights, different weights that we have, and these matrix operations, matrix multiplication particularly, behave like a small rotation matrix. Okay, rotation. So each time a folding happens or the bending happens, and then it's rotated, and again bending happens, again it's rotated. So the idea is internally you will use simple activation functions. So these activation functions need not to be accurate or exactly true what we want to, but in togetherness, once you start doing it 3, 4 times, 5 times, and this is where these things become deeper because so the final layer or the last layer is called the output layer. The initial layers are called input layer. And all the layers between them are called hidden layers. But once you have more than one hidden layer, the learning is complex. Okay, and I can show you with a very good visualization as well that the learning is going to be complex and we will be able to get an outcome. We will be able to get an outcome which will be definitely non-linear. Is that okay? Okay. Very good. So actually, why don't I show you with a visualization? So there is something called TensorFlow Playground, and I personally enjoy at least looking at the visualizations. Let me give you this link so that you all can play around with this. Don't worry, there is no coding involved. It's just the design. Like I have to design things and try to understand. So let's remove the hidden layers. Let's have only one hidden layer, okay? And I could use, let's start with something linear. Let's say there is something called linear activation, okay? Now, let's say I provide the data like this. Okay, so let's increase the training data a little bit. Okay, and let's also put a little bit noise in the data. So, okay. So guys, do you think this would be linearly separable? Can you see the data, by the way?
Yes, sir, we can see.
Does it look linear or non-linear to you? Tell me. Okay, so this looks non-linear, right? Very good. Now the problem is, let's say I have linear activation, I have a singular layer, and let's run this. Now you can see the training and you will see the color changing and everything. Like it will try to show you some kind of a boundary scenario, but it will never be achieved. You will see that it will never ever achieve. Okay, now let's introduce a non-linear activation like tanh, sigmoid, or relu. And let's say I introduce relu. And you see here with just like one layer, because again, Relu has introduced a non-linearity. Within one layer, you are able to see it has been able to come up with a shape, which is as good as, I know there is some noise, okay? I know there is some noise, but still it has been able to segregate. And within this scenario, you can see that initially, yes, the data or whatever information is coming looks linear, but once it is applied with ReLU, and again, in the output layer, there is another activation, or maybe it's just ReLU itself, it is able to segregate it very easily. Yeah, all of those is just happening, and like I'm just gonna stop them like epoch number. Whenever I feel that, okay, it looks like the classification is done, more or less done. So here, as you see, once I start putting the activation functions, or if I start putting the nonlinear activation function, you see it is able to solve this one. So you might think, okay, then single layer is enough. But the problem is a little worse. Okay, what if I create a much more complicated data? Then what would happen? Because that was still very simple. So let's see what happens now. Now here you will see the classification is not that easy, because this data is much complex than the previous. See, it's kind of stuck. It's not able to solve this. So now one technique is you increase the number of layers. See, activation is the same. Okay, I have just increased the number of layers, or maybe the number of neurons. Although this is a big discussion like how it should work, but let me show you what happens now. Now again, it will take time. I'm not saying it will be fast. It's still gonna be taking some time. Okay. Now you will start to see a little bending has started to happen, but let's see. Let's wait for a minute. Yeah, it will. And this is why regulation parameters and dropouts, a lot of other techniques are required. But right now I'm trying to do a very small demo to explain like what really the neural network is able to do. Now you can see it is trying to play that balancing act. Okay, it is trying to balance the data, balance the distribution as much as possible. So let's stop here. And you can see this has become a little bit more complex than the previous one. This has become pretty more like complex than the previous one that we had. And maybe if I take ReLU or something different, let's see if that changes anything. ReLU will work a little faster than tanh. it will be a little faster learning rate. If you understand gradient descent, you will know the learning rate parameter from there. Okay. And you can see that here again, it is pushing it and it is trying to come up with a complexer decision boundary. And this is what neural networks intend to do in long run, as a matter of fact. And these multiple layers. Okay. Anyways, I can stop it right here. You can see still it has not solved the thing fully, but you can see that it has become very, very close. So this is the thing, guys. You have to use nonlinear activation and you have to use multiple layers, or this is why it is also called deep learning, because they are able to learn deep or complex representations. And this will happen when you will use nonlinear activations, and you will ideally have to use multiple layers. If you try to do it in a single layer, it's mostly not going to happen. Okay. And here you can see it is going very close. I'm not guaranteeing that it will happen all the time. Maybe I still need to increase the number of layers that we have here, right? So all of that still is in very much in the play itself. Okay. So once we go there, and you can clearly see, so actually, you know what, I'm gonna draw this for you guys. It is like you are applying these functions, as I told you, at multiple levels or multiple steps. So let's say you have your input layer. So what is happening is each one has its own weight matrix. Okay, let's say this is W1, let's say this is W2. And all of them have to be connected with the previous node. So let's say this one will be W1, 1, 1. So let's say this is 1 and this is the node 1, right? This is 2, 1. So this will be W1, 2, 1. This is 3, W1, 3, 1, and so on. Okay. And this will same as you can imagine here. So maybe this will be called W1, 1, 2. And this will be W2 or 2, 2, because this is the number 2 here. And W2, 3, 2, and so on. Okay. So these weights, each of them is different. And for, again, understand, for each of them, there is a separate bias term as well. So this could be B11, and this would be, there's a B12, and so on. Okay. So they can also be arranged in a matrix format. So the way we write or represent is, of course, we try not to do it for singular variable. Here we use something called matrix, as you might understand. If you have large number of such data, you should use matrix. So you will have weight matrices like W1, Ij, okay. Input in the output or input into the next layer's dimensions. So how would you write it? Let's say it would be like W1, 1, 1. It will start from there, W1, 1, 2, and so on. Okay, and then it will come down, and here it would be again W1. But whatever is the number term over there, let's say it is I into 1. And the final one would be W1 Ij. Okay, this one would be W1, let's say 1 and J. Okay, so this is like a matrix, and your data X would also be represented, Xi would be represented as a matrix or array, let's call it array, X1, X2, X3, Xn, or Xi actually, because we have high dimensional data. And the bias would be represented, so bias would be with the inner matrix or inner array. So B of J, and again for each one of them, B1 of 1, B1 of 2, and all the way till B1 of J. So at the first step, what's going to happen? The matrix multiplication will happen. So the data and the W, so W1 Ij into the data Xi plus B of J. Now guys, you will notice that you will not be able to multiply this. Can you think why? See, in matrix multiplication, if anyone remembers, there is a requirement of conformability. So if you have m into n, then the other one, let's say the first one, so the column into the next rows or the next one should be same. And let's say this is n into k. Then only this multiplication will happen. Okay, then only this multiplication is going to happen. Otherwise, this multiplication won't happen. Yeah, this is called conformability of matrix. So because if you want to do matrix operations, so this is a simple hack here. You can put a transpose here. Now, what would transpose do? What would be the transpose of W1 ij? It will look like W1 j of I, j into I. Okay, it will be rows to columns, columns to rows. And then they become multiplicable, or then you will be able to multiply them with, sorry, actually, let's remove this sign. And then B of j, okay, and then you will be able to add all of them once this flip happens. So to do this flip, you will have to internally utilize okay, and you can clearly see the outcomes here, very obvious outcomes that this multiplication is going to happen. But still, this is still linear. That's the whole thing. This is still linear. But let's say I take this outcome and I say that, okay, fine, you can multiply W1 I into J transpose, of course, X of I plus B of J.
This whole command.
Sorry, what happened? Sorry, what are you saying? Okay. Okay, and then you apply the activation function. So let's say I activate, I put relu here, okay? Relu as my activation function. Okay, so relu looks like this. In the negative space or in the negative side, it is 0. And in the positive, it is basically y is equal to x. Okay, like goes like this. So the negative outcomes or negative values will become 0. And the positives will remain as it is. They will be unchanged. So this is like one of the activation functions. There is something called tan h as well. Hyperbolic tan it is called. And tan h should look like this. Tan h will be between -1 to 1. And this is how tan h goes. Again, fully differentiable, end-to-end differentiable function. And this is again another nonlinear activation function. Someone might like to go with sigmoid only, right? So sigmoid, you must have seen it in logistic regression. So let's say it is at 0.5, and this is how sigmoid goes. And sigmoid will only go from 0 to 1. Okay, and this is 0.5. Okay, this is 0.5. Okay, so there are different nonlinear activation functions we could utilize, but the famous ones are like sigmoid, tan h, relu. Okay, so now the thing is, what I'm trying to tell you is this same step has to be done. So now this becomes your output. Okay, this whole thing becomes output 1. Okay, this is the output at this step. Okay, after the first hidden layer. And then what happens in the next phase? Okay, again, now weights 2 and bias 2 will get involved right here. Weights 2 and bias 2 will get involved, right? So whatever outcome you had now, okay, so let's call it W2 and let's call it J into K. And of course, transposition will happen. And we had output of size J at the first layer plus bias 2. Okay, and this should be of size K as well. And again, you can apply relu or you can switch it up. Maybe this time you will say, okay, this time I'm going to apply tan h. Okay. So you don't always have to use the same one in the regular artificial neural networks. We can change these things. Okay, this is something that we can play around actually quite a lot. So we can go ahead and change this all together as we like. Okay. and our outcome will vary or outcomes will change. And this is like folding that paper again and again. Okay, every time this matrix multiplication happens, a kind of a rotation is happening. You are adding an extra term. This is a translation, and then this nonlinear activation function is applied, which is folding that paper again and again. And the idea is the overall curvature that will come out of it. That would be really complex. And you can see that even by applying few tanh and ReLUs, this is the kind of curvature we are able to get when we have three hidden loops, right? See how complex this curvature has become. It's not perfect yet, I agree, but you can visualize that how complex the curvature has become. It has completely become like this. And maybe after some time, it might be able to run the whole thing or understand or kind of figure out the whole thing. Okay. And again, at every step, we were just applying ReLUs step by step. Okay. So this is something that's beautiful about neural networks, that this function approximation, I think we told you like this is like pattern cognition, right? You should always think whenever someone says like, okay, we are talking about machine learning, you should always think about they are just simply saying pattern cognition. That's all they are really saying. Okay, so this is something that will work in our favor. And the idea is it will be able to learn these complex functions, really complex functions it can learn. Now there could be a question, okay, but how do you know? But then fundamentally anyone can come and say that, okay, that all seems perfectly fine, but then there is a problem. How do you know the right set of weights and biases? See, X is the given one, X is the input and Y is the outcome, that we know. But then aren't we saying that we need to know the weights and biases? How would we know these things? Okay, so guys, the idea is very similar to where the regression works. Yes. The idea is very simple. Okay, so let's say initially the weights and biases can be randomly initialized. So let's say the weight is randomly initialized, random initialization. And you will go all the way till the final outcome where Y or where you can compute the loss. So this final outcome, let's call it Y hat or logit. Okay, you can also call it a logit. And basically you will compare the loss here. Okay, you will compare the loss with the true Y. Now guys, if it is kind of a categorical outcomes that we are dealing with, a metric that we use is something called log loss. I hope you remember this from logistic regression. Okay, so whatever the outcome has come out, the final one or logit of Y, I can call it. Okay, let's not say logit here internally. Let's call it Y hat internally, multiplied with Y, and negative sign needs to be there, log E of course. And this is how you can get your log loss. Okay, and log loss kind of looks like this. And people who might have attended any machine learning seminar or webinar by us, they might know something about something called gradient descent. Okay, so log loss functions could look like this. This would be true for less y is equal to 1. Log loss is also called binary cross entropy. Okay, and this will be true for y is equal to 0. That's a simple trick. Okay, that what you do is randomly you start anywhere, and then what you start doing is you start taking these small paths, which is called gradient descent. Iteratively, this will not happen in one go, of course. It might take time, and these small paths keep going. Okay, it will come down. It will come down step by step. Okay, so this is your binary cross entropy. I can give you the complete equation if anyone wants to note down. So it can be called BCE, binary cross entropy, or log loss for two classes. It usually goes like this: 1 by m. It is to average out all the number of points, and yi into log e of y hat plus there is the other part 1 minus yi, and let me just move it out, dot log e of 1 minus y hat. Now this part works when y is 1, and this part will work when y is 0, the true y. Okay. And based on this, you can call it binary cross entropy. People like to call it log loss. That's all same thing. Okay. This is the same thing. And the overall idea is to minimize the log loss or minimize the overall loss. Okay. So what happens here is, if you want to note it down, please go ahead and note this down if anyone is interested in all that. Yeah, how many number of rows? M is basically number of trained records or number of rows of data, right? Rows of data. Or you can call it training data. That's also fine. Okay. So guys, intuitively what's going to happen is, so let's go back to the neural network. So let's say in the first pass, so this is called forward pass. Okay, this is called forward pass. Okay, and let's say there is output layer. I will just keep it simple so that visualization do not becomes too complex for us. So in the forward pass, the multiplication of, let's say you have xi, you have weights and everything, right? Plus bias and whatnot. All of that will happen. Activation functions will be applied, and same thing will happen at this layer, W2. Here you will have bias 2, this will be bias 1. Okay, but then the final outcome will be presented. Okay, you can call it logit or you can call it y hat. But here I'm saying, okay, we will calculate our loss. That's the log loss that we were talking about. Okay. And this loss would be back propagated, because see, now we have to ask this question if you do it multiple times, right? Who is responsible for this loss? Who is causing this loss? Initialization is yes, random weights and bias initialization, perfectly correct. But that will not give you that mostly, and that is what's the mistake, right? That is where the issue is. But the issue is I do not also know what are the right weights and biases. But with the data, and this is the supervised training idea, we would want to correct this. So the idea is, let's say you want to minimize the loss, or you want to reduce or change the weight. So let's say for W2, I will just give you simple equation here. I will not get into the whole mathematics of it because this can become multiplied with alpha. Now, alpha is your learning rate, okay? The learning rate that you saw over there, into DOA L. L is basically your loss by DOA W2. And what will happen for bias 2? Bias 2 minus alpha, DOA L, partial derivative, by bias 2. Okay. And this will update. And of course, it has to happen iteratively. It will not happen immediately. Okay. Now, what about W1 and B1, guys? They might also be equally responsible, right? Because they will also randomly initialize. So how would we correct W1 and B1? So the problem is loss is not directly defined in terms of W1. So you cannot directly use that formula, but intuitively you are right. You would try to do something similar, but you cannot do this derivative directly. That will not work. Exactly. Now you notice the right thing, but I could make an argument. See, W1, W2 and B2 are totally dependent on the output 1 that they came out, and output 1 is dependent on W1 and B1, right? So anyone remembers the chain rule of differentiation from mathematics? Chain rule of differentiation says if y is a function of x and z is a function of y, and if someone asks you to do dz by dx, how would you do it? You would say it is dz by dy into dy by dx. This is called chain rule of differentiation. Anyone remembers this? Okay. So what we will do is W1, of course, it's true that we cannot do it directly. I could do with differentiation with, let's say, W2. W2 differentiation will happen with, let's say, output 1. And output 1 differentiation should happen with respect to W1. And this is called the chain rule of differentiation. Same thing for beta 1, B1, sorry. B1 existing value minus alpha DOA L by DOA, let's say, let's call it B2. Okay. Okay, and B2 is again also, that's also kind of correspondent with, oh, actually there's O1 by the way. O1, DOA O1 is dependent on DOA B1, right? And this is how the differentiation will keep on happening. And this can be extended, this logic can be extended to multiple layers. Okay, this logic can be extended to multiple layers. And this is what we intend to do actually at the end of the day. Okay, step by step, we try to reduce the loss. So the objective is to reduce the loss or to minimize the loss. Okay. This is your global objective. This is what you are trying to solve. Is this part okay? Okay, very good. So this is your primary structure of a neural network. I know like we are covering all of this in like very, not with that many details, but again, I cannot go in details because this takes hours to explain every step by step how each equation works. So we cannot go in all the details. Yeah, then that's the whole point, that you will get extremely complex function like this. But the problem is you cannot explain this. It would be very hard for you to explain the function because you do not understand the interpretation of what these WN bias values are going to have. But yes, that's the whole plan. This is where interpretability lacks. So again, it is a kind of a trial and error. Like upfront, like if you present me a new data, I always will start with a simple algorithm. Let's say I will start with logistic. I will start with maybe decision trees, random forest. But if the simpler or classical machine learning algorithm do not give me a good performance, then only we should actually look into the direction of neural network. Okay, there are some constraints. We'll talk about that right now. Okay, but go ahead. Any other question? Achha, bias term is very similar to what you had in logistic regression or like linear regression, right? You had your mx plus b, right? Bias term is that just intercept, that extra term that you're adding, and this will allow for a translation effect. So I'm not sure how many of you understand these vector translations and everything. So the matrix operation, let's say this is your original vector, okay? Let's imagine this is your original vector, and this is a vector, okay? So the addition usually means, addition will simply mean the direction will remain same, okay? Addition does not alter the direction, but it will lead to a linear translation. You guys can see it has been linearly moved. Let me write it let's write it down, or let's call it new. So addition, let's say you adds plus b, right? It will just simply move it on x or y direction, and the simple translation is going to happen, but it will not change its angle. Okay, so the m or whatever tan theta you calculate is going to stay as it is. Okay, it is all like very rudimentary coordinate geometry and everything. But if you were to do multiplication, matrix multiplication, what happens? The A, if initially A is here, it can rotate. It can rotate to some new position. So now maybe this is the A new. This was the original A, and this will change the theta. That's a guarantee. Let's say this was starting, okay, this is theta 2 and this starting was theta 1. So rotation does changes the angle, or sometimes it can also cause translation, depends how the matrix has been built. So that is what bias is, kind of adding the term, moving the in translation, kind of a linear fashion. But that's also required, like in terms of line itself, if you think about it. No, Rajiv, it is just an example. Again, as I told you, the actual mathematics will become a little complex. If I actually started to do matrix operations right in front of you, it will take time to do all of that. Okay, it's not that it will always go to y-axis. You don't even have to think x and y here. You could have large amount of axes, guys, because in real data, the amount of dimensions that we might be dealing would not be simply x and y. The problem is you will not be able to visualize any of this. Okay. Yeah. Any other questions? Yeah, and that's all it is. It's all matrix operation or tensor information. And I told you now, the critique of the Perceptron was written by 2 mathematicians at the end of the day. So all of this that is done, the operations that you have learned, it is nothing beyond like your 11th and 12th, like in India, like we have our 11th and 12th. It's that mathematics. It's nothing even very complicated mathematics we are talking about. Okay, even the calculus is taught at 11, 12 level. So we know that the chain derivatives and all that. So now to code these kind of neural networks, as I was telling you, TensorFlow or PyTorch is required, but we are not going to go through that right now. Today, I'm going to just give you a small initial look on a small Python code, which has been written from scratch in NumPy and basic Python, Matplotlib. So nothing very complicated. Okay, if you know your basic Python, it should be good. But don't worry, even if you do not know, it is just for understanding purposes. That's all we are really trying to do. Now, what I'm going to do here is I'm going to keep it very simple for you guys. And yes, we will have some simple assumptions just to give you the explanation properly. So guys, we will start with two input layer or two input dimensions because you will have only two just to draw these things. And this is going to be a classification task. So classification is also going to be binary. So the outcome is also going to be 2. Now this middle layer, we would try to make, or we will specify how many number of nodes we will have at the runtime. Now all these connectivities will be made. Okay, all the connectivities will be made and weight multiplication will happen. So I will try to show you in the simplest way possible how all of this is even working out. Let's change the color for the other one. And when I say full connectivity, it means a complete matrix multiplication. Okay, all the previous nodes and the next nodes are interconnected. Okay, and you have set of weights. So this can be your x1, this can be your x2. Okay, and this is your final outcomes. Okay, these are your final outcomes. So this is how the neural network would be. And again, this is not a deep layer or something like deep neural network. It's a simple artificial neural network. And this should be the last step. One moment. Okay, makes sense what I'm trying to do. You will have weight 1 matrix here and B1 array here. You will have weight 2 matrix here and B2 array. Okay. So this we will use for classification purposes. Okay, classification. And let me show you the data upfront that how or what it will look like. So guys, this is how the data will look like. So what do you notice about this data? Yeah, it's a non-linear one. Right. So this is not going to be easy. What I'm trying to say is I'm not trying to give you a simple data which can be segregated through a straight line. So you will ask like, okay, what is the need of neural network? Because you can come up with a straight line. It is not going to work. Okay, you can try this. It's not going to work. Okay. Okay, let me show you what we will do and how will we do it. So guys, I'm going to use simple NumPy, SciPy just for one thing and Matplotlib. Okay. Harsha, beyond 3D is not going to happen. You will not be able to visualize. That's the complexity, right? You do not know these things. Otherwise, it would become a little easier for us. Okay. So guys, here we are defining a class configuration where we will have input dimensions, output dimensions given, and we'll have epsilon, which is same as alpha, and there is going to be a regularization term. Okay. Because regulation term, because particularly it's required because neural networks have a very bad habit of overfitting in these scenarios. Okay. So we should ideally provide some kind of a scenario, or we should be working in a scenario where we could regularize or we could stop the overall overfitting scenario. Okay. Now I have created a couple of functions to create the boundaries. Okay. So you don't need to understand this right now because again, I cannot assume everyone already knows matplotlib. Okay. Now major mathematics is done here. Okay. The major mathematics is done here. So first, model is nothing but a dictionary for us. Okay. Model is nothing but dictionary for us, and W1. All of these will just contain the weights. Okay. So these will be your matrices. And they will contain the weights. Let's say W1, B1. B1 is going to be an array, and let's say W2. Again, a 2D matrix. And B2, right? Okay. W1, B1, W2, B2. Okay. So in the loss calculation, we are going to pass our model X and Y. Okay. X is going to be the input, Y is going to be the outcome. Okay. And we have W1, B1 for the first layer or the hidden layer, and WB2 for the outcome layer. There is no W1 or B1, or weights or biases for the input layer. Okay, that is just meant for data. There's no outcome over there. Oh, sorry, there's no weights and biases involved in that layer. Okay, now how the process will be. Okay, so let's say you will provide some data, let's say X. Now we'll do a dot operation with the weights. Okay, so let's say W1, and the dot operation takes care of the transpose automatically. So you do not have to do anything here. Okay, plus bias. Understand this one is by default transposed here when required. So this will be the first step that is done, but that is not all of it. You will have to pass it through some nonlinear activation function. Let's say I choose tan h here. Okay, tan h, hyperbolic tan. Okay. So in the next step, what do I do? Okay, so first here till here we have just dealt with the first layer. Okay, we multiplied it, added with the bias, then applied the activation function. Then we move on to the next layer. Again, do the similar thing, but this time weights have changed and bias have changed because this is the outer layer. Okay, outer layer where you have W2 and bias 2. Okay, and here we get our score. So this time we are going to use a activation function for the final outcome, which we like to call as softmax function. Softmax goes like this. For each class or as many outcomes you have, we take the input and provide it, pass it over exponential function and divide it by the summation of all of them. So the outcome will come between 0 to 1. Okay, the outcome will come between 0 to 1, and it is a probabilistic interpretation at the end of the day. So I'm implementing a softmax here. Okay, these two lines are just meant to implement a softmax function. Okay. So first we pass the information. So all of these steps that we took is just to pass the information in a forward pass. Forward pass. You can call this a forward pass. Okay, the information is just getting multiplied and added and going forward. Then what we do, we actually calculate the log loss. This is the log loss calculation. So you do the forward pass, then your loss calculation will happen. Okay. And then we add the regularization term. So this is your L2 regularization. So L2 regularization or any kind of penalty is actually just added on top of the loss function. So whatever the loss is, they will just add it up on top of the loss function. So you can see on the data loss itself, they're just adding extra terms, okay, which is basically L2 penalty, and that will be averaged out. Here, the average out of it is happening. So whatever is the data loss added with the regularization term, then we are averaging it out, okay, divided by the data size. And this gives you the final loss function or loss value with L2 regularization implemented over. Now, if I had to create a predict model, what I need to do is I just need to do forward pass. Let's say the model is trained. Okay, model is very well trained, and let's say this is the input and this is the middle layer or the hidden layer. Okay, and then this is the outcome. Okay. And this is your outcome 1, or maybe you can call it outcome 1 of 1, outcome 1 of 2. So what happens is, if the weights are trained, or we know that weight, we have done the training, we are done with the training weights 1 and W2 and B2 are trained as good we could have. Now, if you wanted to make a prediction, let's say you come up with a new point or the test data point, okay, then how do we do this? Okay. So what you do is you just pass the information forward and you get the outcomes. Okay. There is in prediction phase, there is no error correction. So we do not have to correct any error in the prediction phase. So here again, we will capture W1, B1, W2, B2 from the model. We'll do all the forward propagation. So till this point, you can see we are just doing the forward propagation. We get the probability. And the outcome, okay, so you have two outcomes. Okay, let's say you have two. So one is this, okay, which there are two nodes, right? So let's say you get outcomes like this, 0.87 and 0.13. So guys, what should be your class outcome? Like what class it belongs to? Zero, right? Or yeah, so how would I get this? I will use something called Rmax function. Now, what does Rmax function do? Props is an array, basically. Props is an array. So if I apply Rmax function, what would be the outcome? So Rmax returns the index of the highest value. Okay, max will return the highest value. Rmax will return the index of the highest value. So guys, if it returns the index of the highest value, what is going to be our outcome? 0. If the array was like this, if the outcome array was like this, 0.19 and 0.81. Okay, What would have been the outcome here? 1, because 0.81 is the highest number here and the index of 0.81 is 1. And this is how you actually get the classification outcomes as 0. Okay, done. Now that was loss calculation. This is prediction. Now the next part is how to build the training model. Okay, now here a couple of things have to be added, like how many hidden dimensions you want, right? How many number of passes. So this is your loop. Okay, loop, how many loops we will run with. Do you want to print the loss? So we will put a code, and this is like a flag value. Okay, so flag values just need to be true or false. That's all. Okay. So inherently what will happen here is to actually do the training. First, the forward pass needs to happen. Forward pass. Then you need to get the loss and derivative particularly. So here we are getting the derivatives. Okay. Where here we are factoring in the regularization term because that has to be done, factoring in regularization terms. Okay, so this step by step we will do this, and you can see we are doing it in a for loop. And then the gradient descent updates. So this is your gradient GT update. Then another important steps, the new values like B2, W2, B1, W1 needs to be written in the model so that in the next step, the new values are utilized. And after every 50 epoch, not epoch, let's call it iteration. After every 50 iterations, we will be returning the loss value. So ideally, the loss value, if the training is going right, the loss value should come down. Okay, the loss value should come down, and it will return the model. Okay, once the training is done, it will return the model. Model is that dictionary that contains W1, W2, B1, B2. Now guys, there's a concept of mini batches where we do separation of the data, and let's say we have 1,000 data points. Okay, 1,000 data points. So we can create a mini batch of, let's say, 100 data points. Okay, so the chunk size is, let's say, 100. So how many mini batches we will end up creating? 10 mini batches. Okay, and this is the sample mini batch code. We'll basically take the data, randomly shuffle it, and then we'll keep creating mini batches one by one. And on each mini batch, we'll run the training separately. Now in the main function, what we do here is we make a small dummy data set from make moves. It will come up with circular data sets, but you can make it complex. Okay. And then we will start with W1 and W2. You can see both of them are random initializations. For bias, actually, random initialization is not really a priority. You can see we can initialize them as 0 itself. Okay. But whatever initial values we have, we put them in the model, which is a dictionary. Okay. Now we run this batch iterator, which will produce the batch data chunk by chunk, one by one. And what will happen? And you will be able to see this, that. So this is the initial data. Okay. This is the initial data. And what happens for each batch, it starts the training. So you can see after at 0 iterations, 50 iterations, 100, and so on. And after like 500, it will jump on the next batch, next mini batch. And the training will keep on happening. And ideally, you will see the overall error value or the loss value is coming down. So it means the hope is the training is going in the right direction. And once the training actually happens or finishes, so let me show you. I have also printed out the weights. Okay, once the training is done, what is W1, what is B1? So guys, all the fight or all the struggle in these regression based models or like even neural network based models is to determine these parameters or set of parameters. So this is your W1 and then this is your B1, right? B1 array. And then you have W2 array. And then you have B2 array. Okay. And guys, this is the final classification boundary. Guys, does it looks, has it gotten the work done? Okay, yeah, it looks like it is actually doing a very, very good job. And this is where the state of the art performance happens. Then actually, see, I did not require mini batches. In all honesty, in this example, mini batches were not required. But what will happen in real world is you will deal with, so now the problem with neural network is they require very large amount of data. So maybe in simple machine learning, you can work with like 1,000 rows or 500 rows of data, and that's good enough. In neural network, we will require 100,000 rows. Okay. Now, the problem is neural network models. Now, these are very simple models, of course. Actual neural network models have become really complex these days, really large models. They take GBs of RAM space, and then you have data, right? So many times training all that and putting them in the video card memory for CUDA acceleration and everything might not happen at one go. So if you try to pass 100,000 rows or 500,000 rows, you will run out of memory. Okay, so that is why the reasoning of many batches is there. Plus, there is also implementational optimization as well. Computational efficiency, yes, that's the whole idea. Yeah, then, so in real world, as I told you, the data sites and neural networks are of massive chunks right now. 2 GB, 3 GB pre-trained models are available. So it takes a lot of RAM actually. So unless you have a massive amount of RAM, like 128 GB of RAM or something like that, you will run into problems of RAM or video RAM memory. And it's better to actually provide them chunk by chunk. Okay. No, Harsha, it's not absolute that it will always increase. Neural network training is a little tricky, but yes, ideally the accuracy should go up, but I know that it actually, that's not how it works. It can actually also fluctuate a lot. But yes, the generic intuition is you should have like 50, 100, 200 epochs to train it well. Okay, very good. Okay, guys. Now, guys, if you found this fascinating and if anyone wants this page or something now, you do not have edit privileges here. Okay, you can just see this code. Okay, you will be able to see this code. Let me just share this file. And if anyone is interested, you guys can have a look and dissect this code and try to do something better with it. Okay. But if you are interested, as you know, as I was also telling you yesterday about Learnbay itself, and I told you that you can come up and join us for the coursework here, and you can enroll into advanced AI. So this is going to be part of advanced AI programs, like this one, advanced AI ML and tech professionals. So this would be like a development course. So you guys can definitely look into this, and you should definitely apply for counseling here. And in scenarios, you can download the whole brochure and kind figure it out that what would be the outcomes and how would you get the overall results here. And they always are starting some new batches. So if you are interested in joining, feel free to join us. And I hope to see some people who are interested into this domain and practicing here. And a lot of students like Preksha was my student, and like Arvind was my student at one point. Okay. And Saurabh Maurya is a student of mine. Okay. Abhishek is a student of mine. Okay. So a lot of students actually have gotten amazing jobs at different points. So you guys should definitely think about joining us. And if you want, please apply for counseling. That would definitely help you out. Okay. Okay, guys. If you have any questions, please go ahead. Yeah, sure. You can send me a request over there. I will connect. No problem. So just search under my name, Amritansh. It should not be very hard to find. Okay, it's a unique name, so you will be able to find Amritansh fairly easily. Yeah, then and I noticed that you have been very consistent with our webinars actually. So yeah, these things are interesting. It keeps me interested. I have been working in the field of studying and working in the field of AI from 2014. So understand, like still I know, and I feel that I do not know a lot of things, and I have to keep learning. And same thing will happen to you as you will start learning in deep and depth. You will feel the same scenario that however much you learn, there is something more to learn, and this is really interesting. I really enjoy teaching and learning and building these things. Okay. Any other question? Yeah. So these days, of course, everything or all the neural network code runs on like NVIDIA A100. Like there are like seriously powerful graphics card available right now at industry level and even at a home scale level. Okay. And these things are running AI training, and NVIDIA is selling, or NVIDIA is making more money in selling these graphics card for AI use cases than the gaming one. And NVIDIA started as meant for gaming, like it still is, I'm not denying it, but it has made far more money in this artificial intelligence world than it is making in gaming right now. And yes, these things are required. Although on Google Colab, you can kind of find some free GPUs. So you can do this, right? Okay, let me show you. You can just go here, and right now I've selected none, but you can select GPUs or TPUs, and that will give you a free GPU for, it's not going to be that powerful, but still you will be able to simulate everything, or you will be able to run all of this. Yes, you should just change the runtime. That's all it's required. Harsha, so I think you first should definitely master your mathematics. You could, I think, see that how mathematics is so important right now. So if your mathematics is weak, then of course you're gonna struggle. So if you should be good with your mathematics. Learn programming. Well, I think Python programming would really be helpful, but any other programming language is also fine. But Python is most regularly used in this our AI world right now. And then focus on getting a full course or something very deeper in artificial intelligence, and particularly. Okay. And this is something gonna help you or help all of us in understanding and kind of working through this. And this is gonna be something that you guys can take it forward. And there are really good books. Like one simple book I could recommend to everyone is called Grokking Deep Learning. Okay, they have tried to explain deep learning in the most simple and intuitive way possible. And I think you all can learn a lot, and you will be able to find this PDF relatively easily. But it's not that hard. You can actually find this PDF very easily on internet. So Grokking Deep Learning by Andrew Trask is an amazing book. Again, it takes a very intuitive view. It's not going to be very complicated or something. So you guys should definitely read this book, and it will give you a fair bit of intuition how things work. Okay. Ashok, any cloud you run, any cloud, AWS, GCP, Azure, does not matter. Everywhere I can run deep learning right now. You can focus on reinforcement learning, no problem. If that's your use case, deep learning and reinforcement learning works really well together. So I think you can definitely focus there. All right. Good, good. So guys, I think Karishma is joining. Let me just see if she's already here.
Yes, sir.
1 minute, Karishma. So Karishma, why don't I make you host here? Okay. So guys, I think I will take off now, and Karishma will talk to you about Learnbay. And I wish you all the best, and hope to see you soon in some future webinar. All right. Bye guys. Take care. Bye-bye, everyone.